Steel plate, 5 centimeters thick, shears apart as if it were nothing more than a sheet of aluminum foil. A shockwave pulses through the structure, a microscopic hammer blow delivering a pressure of 10,000 bar, roughly the weight of a herd of 10 African elephants concentrated onto a single square millimeter. This isn't a bomb. This isn't a laser. This is a bubble of water. A tiny, vaporous pocket, no larger than a grain of sand, collapsing with such ferocity that it generates temperatures hotter than the surface of the sun for a fraction of a millisecond. The metal isn't just bending, it is being vaporized, pitted, and eroded from the inside out by the very fluid it was designed to contain. Most turn away. But here at Surphysia, we decode the math behind the chaos. Let's find out. To understand how a simple liquid like water can tear through hardened alloys, we have to look past the macroscopic world of rushing rivers and spinning propellers. We have to look into the invisible architecture of pressure. We often think of water as a solid, incompressible mass, but it is a dynamic medium governed by the laws of thermodynamics. When water moves fast enough, really fast, the local pressure drops. According to Bernoulli's principle, as the velocity of a fluid increases, the pressure exerted by that fluid decreases. If that pressure drops low enough, specifically below the vapor pressure of the water at its current temperature, something extraordinary happens. The water literally boils. But it's not boiling because of heat, it's boiling because of a vacuum. This is the birth of cavitation. These are not air bubbles. They are vapor bubbles, voids in the liquid filled with nothing but water in its gaseous state. As a ship's propeller spins at high rotations per minute, the tips of the blades move so quickly that they create a low-pressure zone behind them. In this zone, millions of these tiny vapor pockets blink into existence. They look like a shimmering, silvery cloud, a ghostly veil trailing the steel. But these bubbles are not stable. They are born in low pressure, and they are destined to die the moment they drift into a zone of higher pressure. And it is in their death that they become one of the most destructive forces in engineering. The collapse of a cavitation bubble is a masterclass in physics-driven violence. As the bubble moves into a region where the surrounding liquid pressure is higher, the water pushes back. The vapor inside cannot support the weight of the surrounding ocean. The bubble begins to shrink. But it doesn't just deflate like a balloon. It implodes. Because the pressure is coming from all sides, the collapse happens at supersonic speeds. As the walls of the bubble rush inward, they accelerate. The spherical shape begins to distort. Usually, a microjet of liquid forms, piercing through the center of the bubble like a needle made of liquid lead. This jet strikes the nearby solid surface, the propeller blade, the turbine wall, the concrete spillway, at speeds exceeding 1,000 meters per second. A jet of water traveling at 3 times the speed of sound hitting a piece of metal creates a localized impact pressure so intense that it exceeds the yield strength of the material. But it's not just one hit. It's millions. It's a Gatling gun of microscopic water hammers firing thousands of times per second. This is why engineers find massive steel propellers, weighing several tons, with edges that look like they've been chewed on by a giant shark. The metal hasn't been rusted, it has been physically hammered away, atom by atom, until the structure fails. Let's scale this up from a tiny propeller to one of the most massive structures ever built by human hands, the Glen Canyon Dam. In 1983, heavy snowmelt forced engineers to open the spillways to prevent the dam from being overtopped. These spillways are massive tunnels, 15 meters in diameter, carved through solid rock and lined with nearly a meter of reinforced concrete. As the water roared through these tunnels at speeds of 40 meters per second, the sheer velocity caused the pressure near the walls to plummet. Cavitation began. What started as microscopic bubbles soon turned into a catastrophic chain reaction. The bubbles imploded against the concrete lining, punching tiny holes in the surface. Once the surface was pitted, it created even more turbulence, which created even more cavitation. The process fed on itself. Within hours, the microscopic hammers had eaten through the meter-thick concrete and reached the soft sandstone beneath. The water then began to quarry the mountain itself. Huge chunks of rock, some the size of a small truck, were ripped out and spit out the end of the tunnel. By the time the flow was stopped, there was a hole in the spillway large enough to swallow a 3-story house. This wasn't caused by the weight of the water, but by the collapse of bubbles no bigger than a marble. It is the ultimate irony of hydraulic engineering: the faster we try to move water to save a structure, the more likely the water is to tear that structure apart from the inside. The physics inside the collapsing bubble is even more alien than the destruction it leaves behind. When that bubble shrinks to its smallest point, the gas inside is compressed so rapidly that it doesn't have time to exchange heat with the surrounding water. This is an adiabatic process. The temperature of the vapor inside the bubble can spike to over 5,000 degrees Celsius, roughly the temperature of the surface of the sun. For a billionth of a second, the inside of that bubble is a star. This phenomenon is known as sonoluminescence. If you do this in a laboratory with sound waves, the water actually glows with a faint blue light. Every flash of light is a tiny explosion, a signature of the immense energy being released. Think about that. In every pump, every valve, and every cooling system of a nuclear reactor, there is a constant battle to prevent the water from turning into a swarm of sun-hot needles. If a pump in a power plant begins to cavitate, it doesn't just lose efficiency, it starts to vibrate with a sound like it's pumping gravel. That gravel is the sound of millions of implosions. If left unchecked, the vibrations will shatter the bearings, snap the shafts, and lead to a catastrophic release of pressure. In the world of high-performance machinery, cavitation is the cancer of metal. It starts small, invisible to the eye, but it is relentless and inevitably fatal. Human hubris often leads us to believe we can master the elements through sheer mass. We build thicker walls, stronger alloys, and bigger engines. We use supercavitating torpedoes that wrap themselves in a giant bubble to fly through the water at 400 kilometers per hour, effectively turning the sea into thin air. But even here, we are dancing on the edge of a blade. The moment that bubble touches the skin of the craft, the destructive forces are unleashed. We are trying to harness a phenomenon that, by its very nature, seeks to destroy the vessel containing it. Consider the tiger's teeth in a dam's flip bucket. These are massive concrete blocks designed to break up the flow of water and dissipate its energy before it hits the riverbed below. They are built to be indestructible. Yet, under the right flow conditions, they can be reduced to rubble in a matter of days. The water doesn't push them over, it vibrates them into dust. We see the same thing in the valves of our own hearts. Artificial heart valves must be meticulously designed to ensure the blood flow never reaches the point of cavitation. If it did, the resulting bubbles would not only destroy the valve but would literally shred the red blood cells, causing instant and lethal damage to the patient. Nature's power is often measured in the big things, the hurricanes, the tsunamis, the earthquakes. But cavitation reminds us that the most terrifying power often resides in the smallest scales. It is the power of a void. It is the vacuum's revenge against the solid. Every time we hear the hum of a boat engine or the roar of a dam, we are hearing a truce. We have calculated the tolerances, we have smoothed the surfaces, and we have adjusted the pressures to keep the bubbles at bay. But the math is always there, waiting for a slight increase in speed or a tiny drop in pressure to turn the life-giving liquid into a corrosive storm of light and heat. The scale of the energy is hard to wrap the human mind around. Imagine a single cubic meter of water. If you could turn all of the microscopic cavitation energy in a high-flow system into electricity, you could power a city block. Instead, that energy is spent on destruction. It is spent grinding down the toughest materials we can forge. We use stainless steel, titanium, and specialized ceramics, yet none are truly immune. Over time, the microscopic pits merge into cracks, the cracks merge into craters, and the craters become structural failures. We see this in the aerospace industry too. In the turbopumps of a liquid-fueled rocket, like the Space Shuttle's main engines or the SpaceX Raptor, the liquid oxygen and hydrogen are moved at mind-boggling speeds. The pumps must generate enough pressure to feed a combustion chamber that is essentially a continuous explosion. If even a tiny amount of cavitation occurs in those pumps, the vibration would shake the entire rocket apart in seconds. Engineers have to design inducers, essentially small propellers before the main pump, to carefully raise the pressure just enough to prevent the main blades from creating vapor. It is a high-stakes game of thermodynamic chess played at 300 degrees below zero. The irony is that the very property that makes water essential for life, its fluidity and its ability to change states, is what makes it so dangerous. We rely on its incompressibility to move pistons and power our world, but we forget that it is only a few kilograms of pressure away from becoming a gas. And when it transitions back from that gas to a liquid, it doesn't go quietly. It returns with the fury of a collapsing star, focused into a point thinner than a needle. We have spent centuries trying to smooth the path of water. We have moved from wooden water wheels to precision-machined hydro-turbines that can power millions of homes. Yet, the ghost of cavitation haunts every design. It dictates the shape of every ship's hull, the curve of every pipe, and the operating limits of every underwater turbine. It is a constant reminder that we do not control nature, we merely negotiate with it. We build our civilizations on the banks of rivers and the shores of oceans, using the water to transport our goods and cool our fires, all while a silent, microscopic war is being waged against the very metal and concrete we trust to keep us safe. The next time you see a boat's wake, or the white foam of a waterfall, or even the bubbles in a tea kettle, remember the violence hidden in the phase change. Remember that those bubbles are not just air, they are the result of physics being pushed to its limit. They are the sound of the universe's internal pressure trying to find a balance. When that balance is found, it is often found through the destruction of whatever stands in the way. From the spillways of the largest dams to the smallest components of a surgical pump, the lesson is the same. The strength of a material is irrelevant if the physics of the fluid are ignored. We can pour all the concrete in the world, we can forge the strongest steel ever known, but we cannot change the vapor pressure of water. We cannot stop a vacuum from wanting to be filled. And we cannot stop the energy of a 1,000-degree implosion from finding a way out. The history of engineering is, in many ways, the history of learning to live with cavitation. We have learned to use aeration, injecting actual air into the water, to act as a cushion. The air bubbles are compressible, unlike the water, and they absorb the shock of the vapor bubbles' collapse. By intentionally introducing softness into the water, we protect the hardness of the concrete. It is a beautiful, counterintuitive solution. To stop the water from destroying the dam, we must fill the water with air. This balance between the liquid, the vapor, and the solid is where modern engineering lives. It is a world of invisible forces and instantaneous events. We use supercomputers to model the collapse of a single bubble, trying to predict exactly where the microjet will strike and how much energy it will carry. We use high-speed cameras that can take 1,000,000 frames per second to watch the star in a jar as it blinks in and out of existence. Every bit of data we gather is a shield against the chaos. But nature is patient. It doesn't need to win every second, it only needs to wait. It waits for the one time the pump is run too fast. It waits for the one season when the snowmelt is too heavy. It waits for the one microscopic flaw in a propeller's casting. And when that moment comes, the bubbles will begin to form. The silvery cloud will appear. The microscopic hammers will start their work. And the steel will begin to flow like water. The universe is full of chaos, but we are here to decode it. Stay connected to Surphysia.